Welcome back, and now we will do the last video. So we're basically done with everything for the mutation, and all we have to do is actually actually mutate after every generation, and that function is done in the genetic manager. All right, and just want to make clear that I say this is the last video, but I hope people will watch this group of videos, and then I will continue this series. There's still a lot to do. We still have the opportunity to implement speciation, to implement crossover, to implement visualization of the network itself. We still have to do the bonus code along, which is basically doing neat in 3D. And in that code along, what we're going to do is just take what we have created in here and create a new scene with that from blank. So it's a good project to see how we can take this written code and implement it in different projects. Okay, and also if I get a good amount of feedback on this, we can do a tutorial where you won't see me debugging as much, you won't see me doing as much of the fumbling around. It will just be straight to what to do line by line and what each line is doing. Alright, so with all that being said, let's get to it. This is going to be the end of this kind of set of videos, and I hope you guys really enjoyed. Now let's put it all together. Let's go to the, we're going to open up our code, and we ended in the neat genome by implementing the mutate weights. We don't know if this works properly yet, because we still have not called mutate weights anywhere. We wrote all the code and we made sure there's no errors, but well, we made sure we fixed all our errors, but yeah, we don't call mutate weights anywhere. So now let's start calling it. And mutate weights is going to be called from the genetic manager. So let's close out of the neat genome. Let's open up the neat G manager. I'll open that up in my reference code as well. And now, since the majority of our stuff is done, we have to simply create one function which does the mutation. So in this, probably right underneath repopulate. Yeah. So right under repopulate, we'll create the function. It'll be called private void mutate population. So this function will mutate the whole population. And now all neat networks. So this function is what it's supposed to do is going to loop through all of the neat networks, and then it's going to mutate it's going to call the mutate networks that are present in the genome of those neat networks. So your neat network has a genome. The genome has the function for mutation. Okay, and the genome is actually the thing that ends up getting mutated. So we're going to write an interesting for loop. We're going to start off by writing a normal for loop, starting from 0 and going to the starting population, and then we'll modify it to what we need. Alright, so this is a normal for loop that is going from 0 to the starting population. However, we want to make sure we don't mutate any of the keep best population. So all of the fish that are in our keep best population, we want to avoid any mutation on them. We want to avoid calling the mutate genome function on them. So we do that by starting our loop from keep best instead of from 0. So we're simply getting starting the I from keep best, and then keeping I underneath the keeping I below the starting population. All right. So if keep best is 5, we will loop from 5 to 20 when the starting population is 20. All right. So let's get to it. Now we get the neat networks, right, of the ith thing. Oh, all right. Since we had one of the things what we could have done is go dot my genome dot mutate genome, right? That's completely fine, and we can do that. However, another way we might want to go is to call a function in the neat manager and mutate the genome through that. Oh, not the neat G manager, but the neat network itself. So instead of having the .my genome, we have all neat networks .mutate network, and that mutate network function we'll call the mutate genome function. It doesn't really matter which way we do it, but if we do the mutate network method, we can add the create network function in there. So anytime the genome is mutated, we can create a new create the new network, right? So we have a genome, we create the network structure from that genome, then we mutate the genome, and now we have to create a new network structure. So it's a little bit easier to do that when we just call it overall function from the G manager to the network to mutate the genome. Okay, so for that we will have all neat networks dot mutate network. Okay, and this function is not created yet, so we will have errors, but we'll go ahead and quickly move over and create that. So let's open up our neat network. And now in our neat network, we have to create a new public function, which we'll add right at the end of this. And we'll call this mutate network, the same name as we called in the neat G manager. And in this, simply we go my genome dot mutate genome, and we create the network over again so that it is built off of the mutated genome. All right. However, we do still have a problem in this. When we create a network, when we call this function over again, our network simply adds nodes to the new node. It is not reset. Okay, so what will happen is we'll just have duplicate nodes being added over and over again from the node genes, because we don't get rid of the previous structure that we have. We just add the new structure over it. So what we need to do is reset our network before we create it. So we'll add a function for that as well. So we'll call this private void reset network. And this function is pretty simple. All we do is clear the list. So nodes.clear input nodes.clear output nodes.clear hidden nodes.clear and connections.clear, and that will reset our network, the structure of our network, so that when we create the network again, it will be like a blank creation. Okay, it will create on a blank structure, so there'll be no duplications. Now, when we think about it, we really want to call this reset network right before. We want to call it in the create initial not in the create initial genome, but we want to call it in the create network function. But we want to call it first thing before we do anything. We want to reset the network, because when we initially create the network, resetting, clearing the nodes, it doesn't affect anything, so it works perfectly. And then in subsequent generations, resetting the network right when the network is created works because we get no duplicate nodes in every generation. And in the future, even if we want to spawn nodes based on like speciation, we want to spawn fish based on crossover and like mating, then we won't have to worry about resetting the network anymore, because it'll reset on the creation every time. So we'll just reset network right here. Okay, and here's the reset network code again. It's very simple, just clear it all. Okay, and here's the mutate network code, which is just, it's a public function, so we'll call it from the G manager. But all it does is it first calls that mutate genome function we created in the last video, and then it creates the network. So it resets the network and then creates the network from scratch, and that should be good. Now we go to the G manager, and now we just have to call the mutate population function, and we'll do this. We can do this in a couple of different ways, but we'll do this we'll do this in the start, and we'll also do this in the repopulating. So when we get the first generation, there's no point in having a generation that is completely empty, because, well, there's no training. We know that first generation is going to be bad because it has no connections between them. So we might as well mutate right away off the bat and just keep and just not mutate the top 5. Okay, so we'll see that the top 5 in the first generation won't move at all. Alright, so we'll be in the start right here. After we create the starting networks, and this actually should be at the bottom. I don't know why that's above that. Current generation should increment right there. So let me just see. Yep, that's the same thing we're doing. Alright, so now in between the spawn body and the starting new networks, we want to call mutate population. So we start the networks, right? So we create the initial networks, then we mutate the population, so we mutate those networks, and then we spawn the bodies, and the spawned bodies have the mutated networks. Alright? And then the generation increments, because that's our first generation, and everything is looking good. Okay? Now that we do it in the start function, we also want to do it in the repop every single time. I want to do it in the repop right after we set the new population networks. So we keep the ones we want to keep, we leave the ones we want to leave, and then we mutate the population. And the mutate population function makes sure that we don't mutate the 5 best that we want to keep. And then that, everything is basically done right here. Let's try to run it, and, well, let's try to see if there's any errors first. Alright, everything is looking good, no errors. Let's press play. Now before, you see how we still get a lot of movement going on, and that's not actually correct. We don't want, even though some of them might move in the beginning, because we do mutate, we can clearly tell that there's too many edges being created, because they shouldn't move to that degree. And I just remember that we actually, in our neat G manager, so what we want to do is go to the neat G manager, go to the neat genome right here, right? Open the neat genome script, and then scroll up. No. Go to the neat network script, and then scroll to where we initialize the network. You see these edges right here where we created just for testing purposes? These were the edges we hard-coded. We don't want to hard-code any edges anymore, because we want to start with a blank network, right? So when we create the initial genome, we want to make sure the initial genome has no connections, no edges, and then our mutation will add edges and add hidden nodes. and we can specify if we want to have hidden nodes in the beginning, but those hidden nodes won't have edges between them. Okay. So now let's open up Unity. And let's press play now that we got rid of those hard-coded edges. Well, that's not good at all. There's 3 errors, and we got rid of 3 lines. So what's up? Interesting. So when I leave these hard-coded, it's working fine. But when I take these out, we get errors. Why would that be? So need G manager, line 52. Okay, so I just cleared that, and that error went away. Now I'm going to press play and see what's going on. I believe the error is just going to... That's because I uncommented this. Uncomment that out, save, go back to Unity. No errors, clear that, press play. And things are looking fine. I guess that was just remnants of like changing scripts in the middle of if you change the script in the middle of the code in the middle of the editor running, then you get errors. So alright, so comment this out, but don't just comment it out. We can take that out completely, backspace that out, save the network. Everything should be looking good. This is how your initial genome function should be looking now that we get rid of the hard-coded edges. We go back to our Unity. No errors. Press play. And we get errors. How? So sometimes we're getting errors and sometimes we're not. And those are always the worst type of errors. But it's probably happening from one of these awake functions and start functions not calling at the right time. So I know somewhere in the awake, when we do call the when we call this like start, input nodes needs to be set up properly beforehand. Okay, this is fine right here. When we're in the G manager, let's go up to see what we do. Well, the G manager is fine as well. I believe we should change this to awake for now, and then we'll see what's going on if that fixes things. For now, we'll change that to awake and the G manager. And let's go back to the thing. Nope, can't do that. Let's change this back to the start function because of our starting population. It's such a strange error to be getting all of a sudden just because we don't have edges. I'm going to pause this and see what one of the first errors is that we get. I wonder where this was. So in the start function, we mutate the population, mutate the genome, add a random node, and in our add random node, we're getting an error. So something's wrong with our add random node function. So let's go to the genome and see what's going on. The genome, add random node function. Something is not right. Let's add an if statement. If congenes does not equal 0, then we do this stuff. All of this stuff. Because we can only add a node if we have connections to split. If there are no connections, well then of course this is going to throw an error. Because it's going to get random dart range between 0 and 0. So, and then it's going to try to access that. So it's not going to work. Now if congenes does not equal 0, then we actually have a chance of everything working properly. Let's try this again. Clear that. X out of this. Clear that. It cannot be applied to operands of the list congene to int. So let's go back to our code real quick. Congenes.count. Right? Because that was a list, so we want to do if congenes.count does not equal 0. So you guys please add this if statement into the add random node function that is inside the neat genome. Okay, so inside neat genome, go to the add random node function and just add this if statement. With all the code that we wrote in between the if statement. All right, should look exactly like this. This is your add random node function should look like this, and now things should work a little bit better. But I don't know for sure. Let's make sure. Yep. Let's start that again to make sure everything is running properly. Everything is looking good. We don't get that silly error anymore. None of our edges are hard-coded. So I think it's about time that we just kind of sit back and watch a... kind of see if any training is actually happening or not. I won't maximize on play yet. Now we can sit here and watch. Oh wait, before we do that, I also want to go to the food manager. Just up the food to 50 so we see, we just watch what's happening, okay? Sorry about that. My Manjaro is still sticky, but we'll deal with it. We've been dealing with it, and we'll continue to deal with it. So yeah, we'll just now see how things are going. Now, also, you guys will notice we don't get any of that circular motions we were getting to begin with, because those motions take 2 edges. But we simply get like up and down movement because our starting generation also gets mutated. Okay, so now we get circular motion. Finally, this edge right, this fish right here was able to spin in circles. Oof, look at that. It seems we have an error in our code again. For some reason, all the food disappeared somewhere. But it's okay for now. Let's continue to just watch what happens. I'm going to go to Edit and then go to Project Settings to open up the project settings while everything is running. Make that nice and small. Sorry about the jitter. But now in project settings, I'm going to scroll down to I'm going to go to time right here, and in time you guys will see a time scale. The time scale you can increase to make this whole project run faster. If we go to time scale 10, you see the neat fish are going really fast. So let's go 5 and see how this, if any evolution happens, or if they actually are able to catch food. Again, some strange behavior is happening with the food. For some reason, the food is disappearing a lot faster than everything else. We have yet to implement one of the most important parts of this. But for right now, let's just look at how this is running. Alright, we see that new movement is being created. We do get interesting movement right here, where the fish do try to learn to avoid the walls. But the fish cannot actually see the food yet. So while our fish do get better at avoiding the wall, they do not get better at getting the food as much. They randomly get food and they get lucky. So one of the things we will do is add these sensors for the food next. Let's go to the fish controller, scroll down to where we have the input sensors, and now we will simply copy and paste this group of lines starting with r.direction down to the loop for the raycast. So these lines, copy those and paste them. Okay. Now that this is the copy and paste part right here. So now we want to change the transform to transform.up. And we want to change wall to food. And we want to change color to yellow. Okay, so whenever the food gets hit, the sensor will change to yellow, and we're actually just adding another raycast. So now we have 4 raycast, and so this is going to get stored in the third sensor. So make sure you copy this part correctly. We change the transform.up minus transform.right to just transform.up, and we change the sensors from being stored in sensor 2 to being stored in sensor 3 now. And now we copy this line over and do it 2 more times. So copy that twice. We will backspace both of them. Now over here where it says transform dot over here for the second one, you guys see on line 124, we're going to do plus transform dot right, and we're going to change this to sensor 4, and now there's going to be minus transform dot right, and we're going to change this one to sensor 5. So now we have the 6 sensors set up to actually see food. And now we have to up the number of input nodes our fish has. Error right here. I already know where it is. Right here. Wrong. What? Change that. Oh, transform. My bad. Form. And that should be right. Instead of fixing errors, I'm creating more errors. But there we go. Everything is looking good. And now the fish should actually be able to see food as well. Ooh, oh, yeah, I didn't. We have to go to the G manager and we have to up the input nodes from 3 to 6 now because there will be 6 input nodes. 3 for the walls, 3 for the sensors. 3 for the food sensors. Now everything is working how it should be, how it was working before. Now we will up the speed to 10 and we will simply watch the training. I think actually, before we continue too far into this training, I'm going to up the food as well to from 50 to 100, because I just want to see that if there's food chasing behavior happening for the demonstration to see if any learning is actually happening. Okay, let's pause this. Because the food is so inconsistent, let's go ahead and fix that problem real quick. Let's go to the Neat G Manager, and down where we do the spawn of the food, right? So when we do the repopulation, we do destroy food. We also want to just copy and paste that. And we want to spawn food. Okay, so we'll go to the food manager real quick. So we'll go to the food manager script. And spawn food is right here. Right? Make sure that that's... Did I have it named? Oh. Make sure that name is lining up to spawn food. And that should be good. Now, whenever the food is destroyed, the food is also spawned. So even if there's like one extra food pellet, it's not that big of a deal. And now let's just have this running. We'll have this running at speed 10 and see how it goes, how the training goes. We'll maximize on play. And now, yeah, I'll up the speed to 10. And you guys can just watch how training goes. I'm keeping an eye out to see if any network is living longer, if we actually see networks that are getting smarter, that are actually going for food. Because that's what we want to see, is networks see food and get closer and closer to it. This one looks pretty good, actually. This guy looks like is doing good at catching food and is doing good at avoiding the walls. As you can see, it's a lot more complex behavior than simply spinning in circles, like a lot of these are doing. There we see another good one. Now, a lot of these, what the networks end up doing is spinning in circles and circling around food. Look at him. Oh, this guy's good. Yeah, he is looking for areas where there's a good amount of food, and then he goes to that area and spins in circles. And look at him. He's capturing a very decent amount. This is one of the good networks that is going to end up getting stained. But this network is an example of actually learning neural networks. And this network here shows how the implementation of all the code, all the hours we've spent actually is creating a trainable neural network. Okay, so we do slowly get closer and closer to a solution. Sometimes we lose that solution, and sometimes we find a new solution, and that's the whole point. Right now, we don't have crossover implemented. We don't have a lot of the things that we should have implemented yet. So that's why we see loss of solutions. But again, after mutation, we usually find a solution again that is able to survive, which is what we're seeing over here. He's not very good at surviving, definitely not as good as what we had before, right? So in the ideal case, our evolution keeps on going up. But sometimes we lose the solution and we have to restart over again. Okay? And we can fix that problem with our fitness function. We can fix that problem with some different implementations of the genetic manager. However, the neat structure of evolution of topologies to solve problems remains the same. Alright? So we built, during this code along, we basically built a model for NEAT. And this model is able to create complex behavior, as we're seeing on the screen right now. A singular fish is able to clear out majority of the food in an area. And this one's actually doing very good. Now, once we add crossover, this fish's innovation gets fed forward into different beings. As we see, this fish got saved into the next generation, and now he continues to do what he was doing in the last generation. Sometimes, because of the way we have the spawning system set up, the fish will get spawned way too close to an edge, and then he'll just hit the edge, and then his overall fitness gets reset to 0, and therefore they just die. Okay, so actually, right now, one of the main ways how fishes die is by hitting the wall, and their overall fitness gets set to 0. So to do even better on training, so the next video, I might still make one more, and that video is just going to say how we can optimize this to get even better training. But for right now, one thing we can do is go to the fish controller, and where the fish hits the wall, we simply do not remove any, we don't do any damage. Hitting the wall doesn't take your fitness away. Hitting the wall simply stops you from being able to get more food and get even fitter. So that's how we will be doing that for now. Let's press play and see how that goes. Now this time I'm going to change my speed to 20, and then I'll slow down eventually. So now the walls no longer take away from the agent, so when they hit the walls, they still are stored in the safe best. So we shouldn't be losing innovations as much. When we see a solution, we should see that solution again, and hopefully we should even see 3 or 4 solutions coexisting and co-evolving together. Alright, we're beginning to see some complex behavior happening. Now we see 2 good fish, which is different from the last simulation. In the last simulation, we mainly only saw 1 good fish at any given time. And now I'm going to slow down the speed because we are on 20 speed. So no matter what we see, it's not going to look very good. We'll slow down to 5. And now let's see how our fishes are doing. And also, while this is playing, we can keep track of what generation we're on. All we can't do it right now because we're in full screen mode. But when we look at the editor, we can also keep track of how many generations our training is taking and what's going on with our training. So we see that yellow one in the middle is doing better at getting food than some of the fish we've seen. However, we're not getting that many good fish. We get 1 or 2 in any generation which does good, and we sometimes lose the innovation. So these are the things we have to work on. But at this point, we can see the fish are evolving and they are learning. Okay, and if I decide to save the in the example, if you guys saw, I had the ability to save the best fish and then continue building off of the best fish. Doing evolution like that is a really good way to do it because you always have competing fishes. Like in this case, we have one fish that ends up doing really good, but we should be saving that fish and creating like 10 more fishes from that and having those 10 mutate. So that's what I do with the once we start saving fish and saving the brains of each fishes, we can implement something like that. But I'm not going to implement something like that until I get at least like a couple of views on this group of videos. Right now, we're going to end this right here because I think this is a good enough show to so people can actually see that learning is happening. These agents are looking for fishes. They are looking for food, and they are trying to get it. They're just not very good at doing it. So as we can see, this agent is able to clear areas and is able to survive for pretty long as well. However, it sometimes gets lost in the learning process, and also we don't have that many agents competing for food. So yeah. I'm still, before I do end this video now, so before I do end this video series, I'm going, this little code along challenge stuff, I'm going to show you guys the scene and how the neat fish actually see food. So as you can see, this fish right here is seeing food above and to the left, so it's going yellow. But this fish right here isn't seeing food, just seeing the wall, so it's white. So yeah, the fish are able to see food. They aren't able to see each other, but they're able to see the food and the wall. So that's good for now. And then in the future, they will. In the future, I hope to add a couple of more things, specifically speciation and crossover, and also visualization of the brain graph that is being done. Okay. But alright guys, I'm just going to stop talking now for a bit, and I'm just going to let this play. But this is the end, so thank you guys for watching. I hope you guys do comment and ask for more, and I hope all your coding goes well. Peace out.